Okay, apologies, the last clip battery ran out on my video camera, so picking up a little bit from there, so apologies for that. But to kind of get some continuity, right, we were at I think this step. I just wrote in a few of the missing details here, right? This was the expected number of white marbles after step k, and we were discussing this possibility of whether as k becomes very, very large, maybe it doesn't actually go to infinity, right? So clearly the number of total number of marbles in the box, which is nk, right? It's proportional to k, so clearly that goes to infinity. And the question is, maybe this number of white marbles, maybe this eventually sort of stagnates, right, and stops growing, right? You see that this number here is going to be getting smaller and smaller and smaller and smaller, and eventually we're going to be taking a product of just a bunch of ones. So maybe it stops, right? Which would, in that example of that I gave you with Android phones and versus iPhones, right? So maybe one of them just kind of hits this cap and just, people stop buying it, and it just flattens out, and the other one takes over, right? And the other one just grows out of bounds and dominates the market. So that's one question you could ask, and we wanted to kind of get a little bit of a sense of it. I was about to suggest at the end of the last clip to write out this product as a sum of the logs, right? And so this is essentially the same exact thing, right? So then now you have this exponential function with the sum, and the only question you have to ask is whether the series as k goes to infinity can possibly converge, right? If you apply a little bit of a Taylor's expansion here, you'll see that log of 1 plus something, especially something small, is exactly that thing. So, and because this is proportional to L, what we're really asking for is whether this series here converges. This is the sum from 1 to infinity of 1 over L, right? And that, in fact, you may know diverges. And so therefore, mu k, which is the number of white marbles in the box, or maybe the number of iPhones in the United States, right, over time will actually diverge and take over, go to infinity. And then with more complicated analyses, you can start, looking at what is the ratio of the number of white marbles to the number of black marbles. How does that behave like? All right, so here you get a little bit into Martingale analysis. I think those of you who took 160A in the spring have seen Martingale, so perhaps we'll revisit this problem again and look at sort of what is the distribution of the ratio of white marbles to black marbles, or the ratio of iPhones to Android phones, right? So I think the answer is that R infinity is actually going to be a pretty complicated beta random variable, or something similar. And so there's a lot of complexity that comes out of this simple example, and you see some nice applications to economics as well. So just to sum up, I think we're nearing the end of kind of this lecture, right? And we got to look at 3 examples, right? Earned problem number 1 through 3, and the first two ended up being the same mathematically. And the third one was quite a bit different, right? It was time and homogeneous, and had all this intricate behavior to look at. But the takeaways here are basically, how do you approach these problems, right? And my suggestion is always write down the state space of whatever random variable or process you're looking at. Play around a little bit with the transition probabilities for the first few time steps, right? K equals 0, k equals 1, k equals 2. What's happening? Try to get a sense of how this is behaving. Then write out the possible transitions, right? We always write out this x. What could the possible possibilities for the next state be at the next time point? And finally, you kind of get to the point where you can conclude that this thing that you have is either a Markov chain or not. And once you have that it is, you go ahead and you kind of go through these first step transition analysis steps that start with the tower property of the conditional expectation. You take this inner conditional expectation, you compute it, right? Because you have these Markov transition probabilities, you're able to do that. And then you set up this recurrence, then you solve it, and that's it, right? And that's just a process that you get the hang of, right? You start out with plain word descriptions, get toward formalism and Markov chain formalism, and then you can start actually computing something that matters, right? So hopefully that's enough examples for you guys to get going on the homework with, and that's all for this lecture.